previous episodes, we discovered three different orthonormal bases in the state space of one photon polarization. We now know that the state space in quantum mechanics is a vector space over the complex numbers. Because with complex numbers we can represent a phase shift as a multiplication by a scalar, which does not change the physical state. However, the relative phase shift in a superposition state changes the physical state, as we have seen in the last episode. I often use the term orthonormal when I talk about bases, but I did not yet explain how to define angles and length in a vector space over the complex numbers. I'm going to do this later on the next week. Now let's return to the bases we have just discovered. The first basis we have ever mentioned is this. We define the horizontal polarization of a photon as the state 0 and the vertical polarization as the state 1. Any other state we can represent in this basis, like for example the state psi here. The coefficients in the decomposition of the state psi in the 0, 1 basis, alpha and beta, are complex numbers. The sum of this squared modulus, of their squared modulus for a normalized state is 1. Now, since alpha and beta are complex numbers, we can write them down in the polar form. We'll denote their modulus with a and b respectively, and the arguments will be xi and eta. Now, if we rewrite our state with this polar coefficient representation, we can notice that we can take the imaginary part of, for example, alpha out of the scope. This multiplier, e in power ixc, is now applied to the whole state, and we can omit it, since multiplication of the whole state by scalar does not change the state. So the state psi can now be rewritten like this. We have a real coefficient before the vector 0, and the imaginary part before the vector 1 has now the physical meaning of the relative phase shift. Let's denote the angle of this shift, eta minus xi, by just one letter, say phi. Now, with introduction of this relative phase shift phi, we have the following expression for the state psi. Both the numbers a and b are real, and they're not just real, they are the modulus of the original decomposition coefficients, alpha and beta. So we remember that the sum of their squares is 1, because the state psi is a normalized state. The sum of two squared real variables equals to 1. Does this ring a bell? Of course it does. It is just the equation of a circle with unit radius and with the center in the beginning of the coordinate system. And this allows us to represent these two parameters, a and b, with just one parameter, the angle theta. Now, instead of a, we can write cosine theta divided by 2, and instead of b, sine theta divided by 2. You may ask why I need to divide theta by 2 in the arguments of sine and cosine. You will see the answer to this question very soon. Now, having this theta and phi, we can rewrite the state psi like this. You can see that the polarization of a photon in the state space is defined by two real parameters, two angles. Do you remember any coordinate system where the position of a point is defined by two angles? Of course you do. It is a coordinate system of a sphere surface. Imagine that we have a sphere. We put our vector 0 right on top of it, which corresponds to the angle theta equals 0 and phi equals also 0. Now we will increment the angle theta, which will correspond to the altitude on this sphere. Well, actually, the altitude is usually 0 on the equator of the sphere, but here we use kind of reverse altitude, which increments from top to bottom. And the angle phi, which corresponds to the longitude, is 0 for now, the so-called zero meridian. Now, when angle theta reaches pi divided by 2, we have this point on the equator with 0 longitude, which corresponds to the vector plus. And when the angle theta is pi, we have the state on the bottom of the sphere, which corresponds to the state 1. Now, this is why I used theta divided by 2 instead of just theta in sine and cosine. I wanted the state 0 and 1 to be at the opposite points of the sphere. Now, if we continue to increment theta, or if we go to the opposite direction from the top, we can reach the state minus, which is on the opposite side of the state plus. Now, these two basis states, minus and plus, are also in the opposite sides of the sphere. Up to now, we considered the states with 0 longitude, where the angle phi is 0. Let's see what happens if we increment phi. And now let's start from the state plus, because there's no sense to increase the longitude on the pole of the sphere. When the longitude reaches the angle pi divided by 2, we have the state 0 plus I1, corresponding to the counterclockwise rotation of the polarization. This is one of the vectors of rotational basis we discussed in the previous episode. And as you may have already guessed, the opposite point on the sphere corresponds to the clockwise rotation, which is the second vector of the rotational basis. So now we have all these three very important bases geometrically represented on a sphere. And any point on this sphere corresponds to some possible photon polarization with particular direction and phase shift. This sphere is called the Bloch sphere, named after the Swiss-American physicist Felix Bloch. It is useful not only for representing the states, but also for representing the evolution of the states caused by the action of various unitary operators. We will briefly discuss this on the next week. For now, it is important to understand that this instrument, Bloch sphere, is applicable not only to photons, but to any quantum system with two states or two-level system.